So sometimes we have some differential equations that cannot be solved with the other methods we've done. We're going to look at what we can do when we have some differential equations that are first order differential equations that we can want to solve, find the solutions to. And we're going to use this method called solutions by substitutions. And what we do is we take those substitutions and they transform the differential equation into a new equation that can be solved with the methods we already know. So we're basically just taking this differential equation we want to solve and we're making it into something we can actually have the techniques for. So there are several different techniques depending on what kind of differential equation you happen to have. We're going to start off with the homogeneous functions, but there are other functions and other ways we do these. Homogeneous functions are not the same as homogeneous equations, so these are not the same thing as what we've been dealing with before. These homogeneous functions have the property that if you take your function and you replace your x, y variables with t of x and t of y, and then when you go to do some work on that and do some algebra on it, you actually can pull a t to some power out, and you're left with the original function in there. So we have t to the alpha times f of x, y when we did this, looking to see if this is the case. Alpha is known as your degree. And what we want to do is let's do an example to show you what we mean by this. So we have a function f of x, y equals x squared plus y squared. I want to see if this is a homogeneous function. So I'm going to look, and instead of having f of x, y, I'm going to replace the x with tx and replace the y with ty. Now, this is not solving a differential equation yet. This is just trying to see if we have this form. I have x squared plus y squared. So I'm going to replace the x with t times x and replace the y with t times y. That gives me t squared x squared plus t squared y squared. Pulling the t squared out gives me x squared plus y squared. So that x squared plus y squared, remember, was my original function. So that's t squared times my function. So that means it is in fact a homogeneous function. So it works, and that means we can actually look to see how we're going to solve those. So let's go ahead and go back into this idea. We're going to we have this function. I put it in this form. It doesn't really matter which form you put it in. You can do the dy dx and get it back to this form. It doesn't really matter, but we have some function m of xy times dx plus a different function n of xy times dy equals 0. And this is a homogeneous function if m of tx ty is equal to t to alpha m of xy. In other words, we can pull that t to a power out. And n of tx ty can also be t to the alpha n of xy. So again, we're pulling a t to the alpha out. Both of them are t to the alpha, same alpha. If we have this formula, we know we have this, then we can solve using a substitution. And the substitution would be y equals u times x, or x equals v times y. And to decide which one to use, it really just depends on which one might be easier to do in that situation. So let's take an example. Let's solve the differential equation dy dx is equal to x plus 3y over 3x plus y. The very first thing we need to do is prove that it is in fact a homogeneous function, because if it's not, you can't do this method. So let's first look at what is our function. Our function f of xy is x plus 3y over 3x plus y. Again, the definition of homogeneous means that if I replace my x with tx and my y with ty, I should get basically back to what I started with, but with a factor of t to a power involved. So we're going to do this. We get tx plus 3ty over 3tx plus ty. And what I notice in the top is I can pull a t out, and I get x plus 3y in the top. I notice I can pull a t in the bottom out, and I get 3x plus y in the bottom. T to the over t, that gives me t to the 0 power of x plus 3y over 3x plus y. So I notice that that is t0, times f of xy. So that means that we are in fact a homogeneous function. So that means I can now do a substitution. We're going to let, and again, it doesn't matter which one. Let's go ahead and do let y equal u times x. And what I'm going to do with this is if I let y equal u times x, first thing I want to do is I want to take my differential equation I have here and get it in that form of the differentials kind of in different terms. So we're going to rewrite this as this is going to be dy times 3x plus y is equal to dx times x plus 3y. And then I'll just get them on the same side. I'll keep the dy term positive and subtract off the dx term. So I now have it in that other form. Didn't take much to get it there. It's just a little bit nicer form to work with when we're dealing with this. I want to get rid of this dy. So I'm going to go ahead and find out what is dy equal to when y is equal to u times x. So using the product rule, this would be the first u times dx plus x times du. So I just used the product rule. All right. So now we're going to do some substitutions. So the x is not being changed. The y is being written as u times x. It's being substituted in as u times x. The dy is u dx plus x du. The x is again not being changed. The y is being replaced with u times x. Times dx. Dx isn't being changed, equals 0. Now just go ahead and multiply everything out. We get 3xu dx plus u squared x dx plus 3x squared du plus ux squared du. Then we're going to have minus x dx minus 3ux dx equals 0. All right, so now we're going to go ahead and collect any like terms we might see we have. We have a 3ux dx and we have a minus 3ux dx. So we can actually cancel those two out. So those are gone. They're out of the way. The next thing I notice is that I have some dx terms and I have some du terms. So let's put the dx terms together. So we're going to get, or let's put the du terms together first. We have 3x squared plus ux squared du is equal, I'm sorry, not equal. Then the dx terms are plus ux squared. Whoops, wrong dx term. Sorry about that. U squared x. And my other dx is minus x dx equals 0. So we now have this. I'm going to go ahead and get it to where we have the du's and the dx's on separate sides. So I'm going to have 3x squared plus ux squared du equals x minus u squared x dx. And then what I notice is that these two terms have an x squared in them, so I can pull it out. These two terms have an x in them, so I can pull them out. Oops, dx, that's not du, dx. And what I notice is this is separable. So usually when you have homogeneous functions and you do the substitution, you will end up with separable equations. We will have 3 plus u over top of 1 minus u squared du is x over x squared dx. And then all we have to do is take the integral of both sides. So we now know we have separable. We can now do the integral of both sides, and we're good. So when I do the integral of this, I get the natural log of u plus 1 over u minus 1 quantity squared. So the integral of 3 plus u over 1 minus u squared is the natural log of u plus 1 over u minus 1 squared. The natural log of x over x squared is the integral of x over x squared is the integral of 1 over x dx, which of course is just the natural log of x. We're done taking integrals, so we do need our plus c. All right, so now that we've done that, let's go ahead and get rid of the natural logs. So we'll raise both sides to the e. So we got u plus 1 over u minus 1 squared. And we're going to e both sides of this. So we have e to the natural log of x, which is just x, and e plus e to the c, which is just e to the c, not plus, but times e to the c, which is just c. So we have c times x. Over here, when this side simplifies, when we do e to the powers. And then if you want, you can go ahead and solve for u. So u plus 1 is equal to c times x times u minus 1 squared. And then remember that u wasn't the thing of interest to us. Y is my variable I started with. Y was the variable I was working with. So y is my dependent variable. I need to get back to my y's. Remember that we let y equal u times x. So therefore, u is equal to y over x. So we'll do that substitution. Y over x plus 1 is equal to cx times y over x minus 1 squared. Notice here, I can simplify this a little bit. I can think about having this be y minus x over x, and then the squared x's, one of them would cancel. So you get y over x plus 1 is equal to c times y minus 1 over, or do y minus 1 squared over x when I do that simplification. And there is my solution to this differential equation.